Hey class, welcome back. We are taking a look at the one-way Anova test. This is a hugely important test in statistics. The typical one-way Anova test is used when you've got some interval scale variable, such as heights and weights and ages and so on like this, is classified according to some other variable which is often nominal in nature. If it's not nominal in nature, then there's probably a better test to use for that. So for instance, we might have an example here, a question on a survey, which is a yes/no question. Have you ever used a computerized dating service, yes or no? And then we want to determine whether age is related to that. So what we've got here is yes and no, of course, is a nominal variable, and then age is interval in nature, and so we've got nominal versus interval. This is a candidate for ANOVA. By the way, when you're dealing with just two categories of the nominal variable, like a yes/no, there may be a better test to use. So we're going to be looking at two sample tests in the next unit. But we'll also find that there's a certain type of two sample test which is a subset of ANOVA tests, and so we can use that. So it'll serve us anyways well. Usually what we use ANOVA for is if you have three or more categories. If you've got just two, then usually you would go with a two sample test. But it still serves us in that it's under the big umbrella of ANOVA type tests. So let's take a look at an example down here, and then we'll walk you through the theory behind this. This is an important unit here, or part of the unit, which is talking about the theory of ANOVA, and it took me a while to wrap my brains around this, but I'm going to do my best to help you out here to see how this thing works. So a forestry official wishes to determine if the heights of common trees differ from province to province. That is, do Alberta trees tend to be smaller on average than, say, BC or Ontario trees? To test her assertion, she randomly chooses 4 trees from each of the 3 provinces and measures their heights. Now, of course, in reality, that's goofy. I mean, you wouldn't choose 4 trees. You'd choose 400 trees or something like that. But we're doing this by hand, and it's something that, with small numbers, we can show you how this particular thing works here. Okay. So again, practically, there would be a lot more trees here. But the important thing to note here is that the nominal variable are the provinces here, right? So that's nominal in nature here. And then the height of the trees, which are these guys, is an interval variable. Interval, right? So heights of trees are interval. Nominal versus interval, we look and say, that's ANOVA. The hypothesis being tested in an ANOVA problem always looks like this, that the means of the 3 provinces in this case are equal to each other, against the alternative that at least one of the means is not, or is different from the others, so is not the same as the others. Now, when you take a look at this, that sounds kind of goofy that we're testing means when the F distribution, which is what we'll be using for this, is a ratio of variances. But I'm going to show you how that thing all works there. So when you're talking about a nominal variable here, the different categories or classifications of the nominal variable are called, in ANOVA, they're called treatments. So that's the term that I'm going to be using from this point on. Is the category of the nominal variable are called the treatments. So we have 3 treatments. And what you do is you set up your hypothesis so that the mean of the first treatment, which is Alberta, is equal to the mean of the second treatment. BC is equal to the mean of the third. The mean of what? Well, it's the mean of the heights. So it's the mean of the interval scale variable, where we're taking all of the numbers and we're breaking them down into provinces here, against the alternative that at least one of the means is different. So we're not saying that they're all different from each other. We're not saying this. We're simply saying that at least one of them differs from the others. And in fact, what we'll find in this example is that the BC and Ontario trees actually are not significantly different from each other. It's the Alberta trees which are significantly shorter. And if you take a look at the numbers there, you can see that very quickly. This is a contrived example. Now, the question that we ask in ANOVA is this one here. And it says, if you look at all these numbers together, so for a moment ignore the fact that they are broken down into 3 treatments. And the question is, what causes the spread there of those numbers? So you can see that they go from a low of, it looks like 40, up to a high of 102. What is the cause of that variation in heights? So what's the cause of the variation here? And is it because that there's wide variation between the provinces, or is it that there's big differences or variation within the provinces? Let's take a look at that a little bit further. And I want to show you this with some clubs here. So with some clubs, I've got, let's say this one is, well, this looks like a kids club, club number 1, and then this is a teenager club, and then this is an adult club. If we took a look at what the averages are, you'd see that this one would be, somewhere around 9 something. This would be somewhere around 13, 14, and somewhere, in the 30s here. So you would see that there would be a big difference in the averages here. On the other hand, if you took a look at the averages here, you'd find that they're actually probably going to be fairly similar to each other. It's something in the 20s. Now, getting back to the whole question of variability, the question is, you've got numbers that run, in this case, from 6 up to 40, and I've got different numbers in each of these 2 examples here, but I've got the same lower and upper bound here. And in the clubs example, the question is, where's the variability? Is the variability between the clubs or within the clubs? And the answer is that the variability is between the clubs. So what we have is within each club, you've got people of pretty close to being the same age, right? We've got the kids club, we've got the teenagers club, and then we've got the adults club. So the variation is between the clubs, or more generally, between the treatments. Now let's take a look at 3 families. And in this particular case, again, the numbers are a little different, but they still run from 6 up to 40. And the question is, where's the variability? Is it between families or is it within families? And here we would see that the variability in ages is mostly because of differences within the treatments. So in a family, you've got a wide range of ages, in this case going from 9 to 40, 8 to 39, 6 to 39, right? Because you've got the kids and you've got the adults. But if you take a look at the differences between the 3 families, you could see that, well, these guys probably hang out together because they're pretty much the same age, right? The adults are the same age, the kids are the same age, so these are 3 families that hang out together. So there's very little difference between the families, but there is within the families. So that between and that within is really critical when we're talking about an ANOVA test. So the way it works here is that what we do is we say, okay, let's look at all of these numbers together here. And of course we can do this for the clubs, we can do that for the families, and we will eventually go back and work through it by hand with the tree heights. And we want to come up with something called the sum of the squares total. So this is something called the SST. Now, all SST here is that if I took these guys here, you remember this formula? The variance is equal to the sum of the x minus the x bars squared over n minus 1. oh, sorry, that's not a sigma, that is an S, isn't it? Because that is a sample variance. So that would be the sample variance of all of these numbers here. And what we're going to do is we're just going to take a look at the numerator, and we're going to call that thing SST. And SST stands for sum of squares total. So you can see this is just the numerator of the sample variance. That's all it is. Now, don't worry about the n minus 1. When we take the ratios and stuff, they'll all cancel out, or there'll be adjustments for that. So don't worry about that. Okay? But what we can do here is we can take that total variation here, which is this the numerator of the variance formula, and break it into two components. And we break it into two components called the sum of squares between and the sum of squares within. So Ssb and Ssw. So what Ssb is it's how much of this variation here of all these numbers together is because there's big differences between the treatments, or in this case, between the clubs. And then how much of that total variation is because of differences within. So that's what we do, is we break the total variation into two components called Ssb and Ssw. Sum of squares between, sum of squares within. Now, what we do is we take a ratio of those two. So we're going to take Ssb over Ssw. Now, there will be some there's going to be some denominators here. It's degrees of freedom, so I'm just going to put them in like this. We're going to go k minus 1 and nt minus k, and don't worry about that right now. What I want you to focus on are these guys right here. Okay? So we're going to take a ratio then of two variances, and of course that's an f-test. An f-test is a ratio of variances. Now, what we have here then is that if Ssb is much bigger than Ssw, which is what we would have in this case, where the major variation is explained by differences between the clubs, not within the clubs. Very little variation within each club, but a lot of variation between the clubs. Then in that particular case, you're going to get a really high F star value. So I'm just going to say a high F star value. Here's the opposite, where we would end up with a low F star value. And that's where most of the variation in this particular case in the families is within the families themselves, not between the families. So when you take the ratio of Ssb over Ssw, you're going to get a very small number. Now, what does that have to do with means? Well, what we do is when you take a look at the original HO and HA, let's take a look at the clubs and the families. So I'm just going to say, sorry, let's back up here. Okay. So the clubs, like that, against the alternative. That at least one of the mu's for the clubs, we'll just call it the j'th, differs from the others. Now, what happens here? If you take a look at this particular example here with the clubs, what you're going to see is that the means are really different. The sample mean here is somewhere around 9. This is going to be somewhere around I think it's about 13.5 or something. This is, well, around 38 or something. There's a big difference between these. And so a big difference between them, which would be where they're not equal, at least one differs from the other, is when you have a high F star value. So that's what we have when there's big differences between versus within, such as when we've got the clubs. Now, if you take a look at the families, the family means are all pretty close to each other. They're all, I'm going to say there's something like 25. I don't remember exactly what they are, but they're in the low 20s. And so there's very little difference actually between the averages, and we end up with a low F star value because the variation is not between the families, it's within. And so when we take this ratio of between over within, we end up with a very low F star value. That causes us to support the null hypothesis. So if you end up with a high F star value, then we would reject HO and conclude that the means are significantly different. If you get a low one, it actually means that they're not significantly different. What this all entails is that the F distribution actually, the F test, pardon me, is always upper tail. We always put our alpha in the upper tail here. So a low F star is, which is what we would get with the families, just supports the null hypothesis. The means are equal. But when we have big differences between, we end up actually with a high F star, and that supports the alternative hypothesis that at least one of the means are different from each other. Woof, that's a lot. I do want to show you just kind of where we're going here in terms of the calculation of these guys. And that is, we come up with something called the Anova Table. And so what we do is we take the numbers. I'm going back to the example of the trees. So these are Alberta trees, and these are BC trees, and these are Ontario trees. And so those are those original numbers, 40, 50, 45, and 43, back in our original problem. Just take you back there, right there. And what we do is a bunch of calculations here. So you square each number. That's what we would do if we were to calculate a variance anyways, wouldn't we? So think of them not being split up into 3 different columns or treatments here. Just think of them as being 12 numbers together. If you were to calculate a variance, then you would square each number and add them up, and well, you know how the variance formula works there. So what we've got here is the number 40 and then its square, which is 1600, and we do that for every number here. And so what we end up here with is the sum of the original numbers and then the sum of the squared numbers down here for each column or each treatment. Remember, the columns are called treatments here. And then we're going to use some formulas down here. Now, if you take a look at most stats books, they use double summations and they use double subscripts and stuff like that. And the overall mean they call X bar, so it's got 2 bars over top of it, and it's actually really a hassle. So I tried to make this as a little simpler here, and so I'm just using a notation that looks like this. So Cj is just going to be the sum of the X values in the jth treatment. So in other words, it's just these guys right here. It's summing them up. So 40 plus 50 plus 45 plus 43 gives you 178. And then the Cj squared value is just the sum of the X values for a particular, the squared X values for a particular treatment. So it's summing up these guys here, 1600 plus 2500 plus 2025, and then 1849, and that gives you this guy. So that's your C1 value and your C1 squared value. 178 squared is not 7974. Remember that this number here is not the square of the sum, it's the sum of the squared values. Just like when we calculate standard deviations and variances way back. All right, so we do that for each treatment. And then just another thing to note here, we've got NT is just the total n. That's the n that you're used to from before. So whenever we talked about just 12 numbers, that would be n. But the fact that they're broken up into 3 different treatments now means that there's a different n. You'll see it down here for each treatment. So in our particular simple case then, the n for each treatment or each province is going to be 4, but the total n will be 12. So this is how we calculate the SST. And you can see that that's pretty similar to just a variance formula here. And we're just using slightly different symbols and so on. And then we break that up into an SSB and an SSW. So this is how you calculate the SSB, and then this is how you calculate the SSW. What you find is that when people work through ANOVAs, they'll find that it's good to put this all into a table. So what we've got here is we've got an SSB row, and an SSW row, and an SST row. And then the degrees of freedom for SST are NT minus 1. So that's just, again, going back to this formula right here. Way back in your first stats course. Right? So this numerator is just the SST. And this denominator is NT minus 1. But then we break the SST into 2 components, SSB and SSW. Just like we break the n minus 1 into 2 components, K minus 1 and NT minus K. What's K? Well, K is actually the number of treatments. So K stands for the number of treatments, 3 in our particular case for the Alberta, BC, Ontario, 3 actually for the clubs, 3 for the families. Of course, in other problems, it'll be different. And then what we do is the numerator of the F star is going to be SSB divided by K minus 1. That's just an adjustment for its degrees of freedom. And then the denominator will be SSW divided by NT minus K. And that ratio then will give you your F star value. Now, a symbol which a lot of books use is MSB, which stands for the mean mean squares between mean squares within. I usually don't even use that. I just simply use these guys here. Right there. It's just a lot easier to understand. All right, we're going to do an example with this next. And I think this particular lesson is long enough, so we will end it at this point and then pick up the example next day. Thanks for listening.